Okay, here's our outline for today. And we're going to do some clicker questions, so make sure your clicker is turned on right away. I have some news for you, however, which you may consider to be bad news, and that is there's no lecture on Thursday because we have a football game, Florida International University. And so what my hope is that UCF crushes Florida International like a bug. That's right. They can't. They're going to come, but so that's their problem. You mess with the best, you die like the rest. That's all I have to say. Anyway, so that's a long and colorful way of saying no class on Thursday. And I gave the morning class off too, so you guys get a break. It's good. Now, I want to talk about homework for a few minutes. Let's go ahead and, this is going to work, I think. Let me get this little doodad out of the way, though. This will probably be good up here. Oh, you guys can't even see what I'm... Gosh, let me go backwards in time. Hold on a second. How do you do this? How do you go backwards in? How about this? There we go. There's what you were supposed to see when I told you that there was no lecture. You were supposed to start crying like that little baby. Anyways, and here's the picture of UCF football players, so hopefully they'll do good. Anyways, no class Thursday. All right. Now we'll talk about homework. And I want you to be aware that I can see what students are doing at any one time. And so, for instance, when I look at homework 1 reading questions, which is your little teeny assignment over the weekend, I looked this morning and I saw, I could see all the names. I put a little witness protection screen over the names on the students here. But at 7:15, we had 168 who have not taken the test. And then between lectures, I looked at 11:45 and it's down to 117. So hopefully the bunch of you between 11:45 and now have done that homework. And by the way, homework is always going to be assigned like on a Tuesday, and then if I give you something that you have to click inside web courses or something like that, it'll be due the next day, the next lecture. Okay, so if I give you after Tuesday lecture a little assignment like this one in web courses, it'll be due Thursday. If I give it to you on Friday, it'll be a little bit longer period. It'll be due the next Tuesday, like today's was. And it will always be at the beginning of this lecture. So if you're not in this section, if you're in section 1 and you're coming to the afternoon class because you're a slacker or for any other reason, you can't get your homework done. This section, the deadline is 1:30, but the morning section, the deadline is 9 o'clock. So you got to bear that in mind. All right, so yeah, 11:45 things were looking a little bit better. Let's keep going. I want you to, I want to remind you of the diffraction playlist, and in fact, our entire Astronomy 2002 lecture playlist is a separate playlist in web courses. Here's the URL, but don't bother writing it down because it's linked to web courses. And I'm going to ask you some questions about that. Now, if you didn't come to class Tuesday last week for whatever reason, and you did look at the diffraction YouTubes as you were supposed to with homework 1, then you'll be able to do the clicker questions, which we're about to do. All right. So let's keep going, and we got a few other things to talk about. Next, the homework. I want to talk about how homework works. I'm going to try to organize your reading assignments with or without a little quiz inside web courses, similarly to the way I did the Homework 1 headquarters page, the HQ page. Now, if they come with reading questions like we did for Homework 1, nice. But they might not, and it will just be reading and maybe a few YouTubes, maybe like the hyperphysics, one of the simpler pages on hyperphysics, or maybe something inside one of the online encyclopedias through the library, and those work pretty well too. So we'll have additional readings from time to time. Most of it will be in the textbook. And a student asked me this morning, hey, Dr. B, is there an outline of all the different readings? And I guess he's one of these guys. I was never like this, but, he just maps out his entire semester and just, he's like a machine. And, I would love to be able to do that, but this is my first time using this free textbook, and so I'm just like 1 or 2 steps ahead of you guys. All right, but I'm going to try to get them to look like what you saw in homework. So let's take a look at that. To get to the homework pages, you go to the homework list, okay? And that's this link down here right below the big observatory image on the home page, okay? And when you click on that, it'll look like this, all right? There's a green false color image of the sun in ultraviolet, a little blurb underneath there telling you about it. And then over here to the right, you can see, let me see if I got my cursor here. Yeah. Okay, over here to the right. Now, right now we only have 2 assignments in there. Homework 0, which doesn't count zip for your grade, but homework 1 does. It has those questions in web courses. And homework 1 looks like this. Here's the HQ page, at least this is the top of it. All right, so I'll try to get stuff organized and outlined similarly to this. Although now that I look at it, I see that I have Arabic numerals for each level. Look at that. Number 1, the second level is Arabic numerals, but for number 2, the second level is lowercase a, b, and c. Anyways, I'll try to do it. It'll try to look similar to this for our reading assignments. And even though we will not have lecture on Thursday, I will give you a homework assignment, probably just reading, maybe a few questions over the weekend. And I'll try to do that by lunchtime tomorrow or maybe a little sooner. Okay, I'll announce that at the end of the class. Question?
These also be on web courses?
The question is, will these also be on web courses? I don't really know how to answer that because it actually is on web courses. So do I say, no, it's already there, or do I say, yes, it will also be there? But anyways, is this your first day in class? Did you actually? Don't say that. I'm just, because, dude, there's a lot of people that did late ads, so, But yeah, this is in web courses. And, the previous page, this one back here, let me see if I can inch back here. This one over here with this big picture of the observatory and stuff. Dude, look up here, come on. Okay. I'm talking right at you. I'm 15 feet away from you. Yeah, look at that. So that's on the home page, and then down here is where you're going to click. So yeah, the answer to that is it's on web courses. So it's good, and I don't mean to get on anybody's case, but that's the way that's going to work. Another question about homework, because I know there's a lot of you, and it could be and you're nervous about homework and reading and stuff like that. Yes, in the yellow.
So I used the iClicker for an earlier class today, and it has a different frequency. How do I reset it so that I can click for your class?
Dude, that's not a homework question. But I'll tell you how to do it. It's pretty easy, and I've already mentioned it actually in just a minute when we start the clicker questions. Okay. He was asking how do you change the frequency, and I'll tell you how to do that. In back there. Yeah, there was diffraction stuff. There was a page on diffraction and plus we had the demonstration. So, yeah. Mm-hmm. Question?
So, you said you're gonna assign homework like roughly like maybe later today or tomorrow.
Yeah.
Will that be due just Tuesday?
Yeah, it'll be prep. This is a good question, especially if I don't have questions, like a little quiz. If I just give you a reading, maybe a couple of YouTubes to look at or something, if that's all I do, then be ready at the next lecture to answer questions about it. That's why I'm assigning it. Okay? So it'll always be, whatever reading I give you, it's to be ready for the next lecture. Okay? And I've got kind of a rough outline of the semester, but I don't have all the readings lined up yet. But hopefully I'll be able to get you at least a couple lectures ahead starting next week. Okay, so it's kind of tricky organizing stuff sometimes, especially with a big class. Another question. Okay, let's start with a few clicker questions, and we'll review some spectral line concepts. And actually, this is stuff that we talked about in lecture Tuesday, and we actually viewed some spectral line activity inside the lecture hall. This image here is actually from YouTube. And it's from a few semesters ago, different TA and everything. And it should look similar. This is in the big subterranean lecture hall in the Mathematical Sciences building, which is where a lot of the astronomy classes are taught. So this is the thermal light source. It's incandescent. It's producing light because it's hot. This is observation number 1. Now, it's a different lecture hall, so it looks a little different background, but the rainbow off to the left should look familiar. All right, so I'm going to ask you some questions about that. So let's focus in. And I'm going to ask you some questions. Let's see if I can get this started. Okay, here we go. Come on, clicker. There we go. All right, so here's how you do it. If you used it from another class, you press the power button down for like 2 seconds until the little rectangle flashes, and then you hit D and D again, and look at it, and you'll get a Go Nitro message, and then it'll say ready. Okay, so that's good. All right, so let's do this. All right, now your question. Let's see if I can. There we go. Let me move this out of the way here. Okay, so we have a continuous spectrum from a thermal source viewed through a large diffraction grating. Which object in view here, A or B, is the central image? So go ahead and vote. And I can see you, and you guys can see the count of people voting. Where's my cursor? Dude, I've got there we go. Okay, so you can see 150. 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, 172 of you voted. And let's see what you guys voted for. Yep, 78% of you got it right. Dude, I usually have a TA doing all this stuff. Start it again. Let me move this out of the way here. Yeah, B is the correct option. That's the central image. It's not, and just to remind you, it's not a naked eye image. It is the central image. It is a diffraction image. But the central image, all the colors, all the wavelengths of light stay together. But it's the second image out to the diffracted image off to the left and right that shows the rainbow or that shows discrete colors. So let's do another question concerning discrete colors, okay, or discrete spectrum. Here's the same lecture hall, and I guess it's the same session, and we videotaped all the stuff and YouTubed it. This is hydrogen. Let's do a close-up on it. All right, and let me move that over here a little bit. All right, and so there's your close-up. And I'm going to ask you another question. Doggone these cursors, they're messing me up. Okay, that's already done. Okay, so we got a question. Here's your question. Which visible object or objects, plural, form the quantum fingerprint of hydrogen? Now, your red line over here on the far left, that's the one that we called H alpha. The one that we looked at, I didn't give you the name for it, but that bluish aqua line is called H beta. And the two purpley ones, H gamma and H delta. All right. Now they're not in view here in this image, and we got the central image on the far right. So choose, make a selection. Which one forms the quantum finger, or which object or objects plural form the quantum fingerprint of hydrogen? And this is actually a important concept for us to think about. Okay, 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, now this time I'm not going to X out of it. And actually, that's question 1. Oh yeah, this is the question we just did. Okay, most of you got it right. A majority got D. This is the correct answer. Both of those lines together form the spectral fingerprint or the quantum fingerprint of hydrogen. So whenever we see that color combination, we at least know that there's some hydrogen in there. And please make a side note in your notes for the day. Sometimes the surface condition of a star are such that temperature and pressure do not permit all of the spectral lines to show. So you might only, in certain conditions of pressure and temperature on the surface of like a small star, you might get a lot of red, but not a whole lot of purple. Because purple is high energy, red is the lowest energy. Matter of fact, under even lower energy conditions, you might get a lot of infrared spectral lines, which you can't see, but astronomers, we have detectors for infrared lines, and it's perfectly fine. So the full spectrum of hydrogen includes infrared, and I think it has a few ultraviolet and a bunch, these visible wavelengths. And so seeing certain subsets of the fingerprint lets you identify hydrogen and also tells you something about the temperature at the surface of the star. And we'll talk more about surface temperatures in a few weeks. Question here in front.
Oh, I was just asking if you could please repeat what you said about the surface condition of the star, such that temperature, pressure, that's what I lost you.
You want me to repeat that? I don't like, I'm not being rude, but I don't like to go back over what I say because everything is being recorded and YouTubed, all right? So and this gives me a point to encourage you once again, take very basic notes, quick, easy, and then fill them in after you go and hit the YouTube, all right? And if you just have to hit one section where you didn't quite get it, like in your case, it'll take you 5 minutes.
Okay.
And the YouTube will be up maybe 20 minutes or so after lecture, so it should be good, all right? And so if you ask me, can you say that again, Dr. B? Sometimes I will repeat stuff that's important, such as saying that the subset of colors that you see from a star will tell you the surface temperature and pressure conditions of that star. But I might not say it the same way, but I will repeat it as carefully as I can if it's important. But if I don't, just go back to YouTube. Question over here.
Yeah, what does H alpha and H beta stand for?
It just means alpha means the first and primary line in the visible part of the spectrum. It's like 1, 2, and 3, and 4 and 5, but they use Greek letters, alpha, beta, gamma. H refers to hydrogen, yeah. And helium's got alpha lines, and and there's other series. There's ultraviolets. They have a whole series of alpha, beta, gamma, delta, and ultraviolet, and infrared. Water has lines. But H alpha is the most famous line in the universe for us humanoids, anyways. So, okay, let's keep going. And let's talk now about some comments from your reading, section 1.3. And I have comments for the next few sections. Let's go through it item by item. Here's a quote from section 1.3 that I liked a lot. The rules that determine the motion of stars so far away that your eye cannot see them are the same laws that determine the arc of a baseball after a batter has hit it out of the ballpark. Now, that may not seem very bodacious to you, but in the day of Sir Isaac Newton and Galileo, that was big news. All right? Sir Isaac Newton had this insight, and then he created his theory of universal gravitation under the theory that the same force, gravity, controlled an apple falling out of an apple tree as controlled the moon in its orbit around. And he specifically modeled his theory using his knowledge of the moon's orbit around the earth. And it was a bold conjecture. And Galileo actually made similar discoveries. Now, he didn't develop a theory of the universal gravitation of objects in the universe, but he was the one that developed the whole idea of looking through a telescope up at the stars. And so I'm gonna back up a few more centuries to the days of Aristotle and Plato and those cats. Okay, in those days, like the ancient Greeks, they're going around in togas and stuff like that, and they're planning for their part in the movie 300 and all that stuff. Okay, but one of the things that they thought about was the stars and the planets. Now, they knew that the stars appeared to be fixed in their places. And so the Big Dipper never changed shape. And for us in our lifetime, the Big Dipper will never change its shape. Orion will never change its shape in our lifetime. Okay? So they knew that. So for them, they had this idea that the stars were kind of embedded like little sparks of fire on this immense celestial sphere. Now, if you've ever heard that term, celestial sphere, it traces all the way back to those guys. And they thought that the stars were fixed in that sphere. Now, the planets they knew, sometimes Mars will traverse through the sky over the course of months through the constellation Virgo and the constellation Taurus and all that stuff. And people have known that since the days of the Babylonians and the Egyptians. All right? And so that's, that was well known. And in the time of the Greeks, they thought that the planets, Saturn, Jupiter, Mars, Venus, Mercury, the sun, and the moon were all on their own spheres, similar to the celestial sphere, and that they moved in certain rates around the earth, and that the North Star was the pole of the celestial sphere, and the other spheres were slightly tilted. Okay? Now, I say all that to point out Sir Isaac Newton's conceptual breakthrough in Part A here, in Note 2A, that the same force controlled terrestrial behavior, a baseball hit out of the ballpark, an apple falling out of a tree, as controlled the moon in its orbit and all the planets. Now, Sir Isaac Newton thought that it was the same force, and that was his force of universal gravitation. But it would never have occurred to the Greeks to think that. They thought that there were two separate laws of nature for the sphere, the celestial sphere, and all the planets, and then us down here. Have you ever heard that word mundane and divine? Divine is up there in the heavenly realms, and it's totally separate from transcending earth. And a mundane, that means the world, mund, M-U-N-D. Mundane means earthly. And the ancient Greeks, Aristotle and those guys thought that the celestial sphere was so perfect, it didn't have anything to do with the mundane laws of chariots and their charioteers and arrows flying through the space and, togas and all the stuff that those Greek guys were thinking about, And so, but Sir Isaac Newton said, no, man, I think they're the same force. And, and really, the guy that made the conceptual breakthrough was Galileo. Now, make a note on what Galileo reported. And it's, this is like, letter 2, E, F, G, H, and so on for Galileo. Galileo, his conceptual breakthrough came with he was the first one to turn a telescope and look at the stars. And he said, "What?" Aristotle, he was a disciple, a student of Aristotle. Galileo was a student of Aristotle. All those guys back in Galileo's day were. Aristotle, if you wanted to learn about physics, you took out Aristotle's physics book. If you wanted to learn about botany, you took out his botany book. If you wanted to learn about philosophy and logic, you took out Aristotle's logic and philosophy books. So he was a student of that, but once he turned the telescope to the heavens, that is when things started to change for Galileo. And maybe before that, but definitely when in 1609, he started observing Jupiter. And he found that there were stars, and he figured out that they had to be moons. And we call those the 4 Galilean moons of Jupiter. And those are the 4 big ones. He discovered them. And so here's a guy that said, whoa, the celestial sphere has moons, just like as the mundane earth has a moon in orbit. He knew that the moon was orbiting the earth. That was clear. And the Saturn or Jupiter up there, the mightiest of the planets, it wasn't perfect or anything. It wasn't even close. It had moons. All right. You know what else? He was able to see the rings of Saturn, but he couldn't figure out that they were rings. He thought of them as like handles on a. He couldn't quite make them out. They were a little bit fuzzy with his telescope. He thought of them as a mug of a handle on a teacup. All right. So, but now of course, a few decades after Galileo, they figured out. Everybody figured out that they were actually rings, and that's kind of cool. Nowhere is there any rings. In those days, rings were totally novel. Another thing Galileo said, He turned his eyes and he looked at the Milky Way. Now, there's all kinds of legends, like the American Indians have legends, and the ancient Sumerians have legends, and the Egyptians probably. And probably everywhere you go, they have a legend about the Milky Way. Our ancestors, where they went to heaven, but one of them spilled some milk, and it ran down through the sky, and that's why we call it the Milky Way. And there's all kinds of, legends of that. But Galileo, so it wasn't, perfection. But, he was able to look at the Milky Way and he said, dude, that's not milk, it's not a fluid, it's not a river, it's individual stars and zillions of them. And that's what it is. And we're in the middle of a disc-shaped conglomeration of zillions of stars, and we're in the middle of it and we're looking at, the edge of it. We're kind of looking through it. So for us, the Milky Way looks like raise your hand if you've ever seen it, the Milky Way. And it's pretty pathetic. Here in Florida, it's really tough. But I'll tell you what, if you go not too far outside of Orlando, in a couple months, October or so, November, you go up to Ocala National Forest and you camp out for the night up there, and hopefully there's no bears running around or anything. And if it's a nice night, you'll see the Milky Way for sure. You don't have to get too far away from the lights of Orlando, but the lights of Orlando wash out everything. It's very hard to see the Milky Way. But anyways, Galileo saw it, and he said, man, those are stars up there, and there's a lot of them. Another thing that he saw, sunspots. The sun in his day was this epitome of pure reason. This like a symbol. It always, wisdom is viewed as light. Your mind is enlightened. Okay, and so the sun was like a symbol of that, the perfection of wisdom. But Galileo, and he went blind eventually, when he was aged, he looked at it with his telescope and he said, dude, there's spots and they change. Now we now know that those are magnetic storms big as the earth on the surface of the sun, bigger sometimes. But he just saw, and so, no, the sun is not perfect. The ancient Greeks, no, you got to have two separate laws. Heavens, those are perfect. Earth is mundane, you got to have a separate set of laws for that. And Galileo said, dude, I don't know about that, because they definitely look imperfect. The sun is not perfect. And that was controversial. Sunspots in his day was controversial. The moons of Jupiter were controversial. Let's see, what else did he see? Oh, the mountains. He took his telescope and he looked at the moon. And you can see by your naked eye that the moon doesn't have a perfect, flat, white face. It's got different shades of gray in it. And they're kind of blotchy and stuff, the man in the moon. And so there were various theories of why that was and so forth. But Galileo and everyone in here, you can take a pair of binoculars, and even cheap ones, like you had from when you were a little kid and you went to the zoo or something like that, they give you a pair of free binoculars. If you look at the moon, and it has to be a half moon or a crescent moon, don't look at the full moon, because the binoculars will intensify the light so much that you'll burn your retina. You'll burn your eyes out, as the saying goes. Okay, so don't look at a full moon through the binoculars that you have. Spotting scope, if you're a hunter. But half moon is fine. Crescent moon is good. And when you do, you'll see that there are mountains on the moon. They cast shadows. It looks like, any other sunny day on the earth. You can see them. We don't have a mountain. For those of you that are from Florida, a mountain is like this pile of rock that rises up thousands of feet. And they have them in almost every other state in the union, but not in Florida. And anyways, actually, I'm trying to think. There's not many states that don't have mountains. And I used to live in Montana. Everywhere else I've lived, other than Florida's had mountains, so I kind of miss them. Anyways, the moon has mountains. So the moon's not this perfect, la la land up there. Oh, everything's perfect and nice. No, it's got mountains. So Galileo, here's another one. Galileo was able to spot with his telescope. He looked at Venus. And he found that Venus is not just a disk. Like the moon is always facing us, but it goes through crescent phases. But full moon is, a circular disk to your eye. Okay, it's a sphere, and it looks like a disk. And everybody thought, Venus is pretty bright every time you look at it. The morning star or the evening star, whichever it happens to be, and it's always really bright. But they didn't know that even when it was really bright, it's possible that they were looking at a crescent Venus. And Galileo was the first one to see that Venus actually was a crescent. When we are outside, when the sun is in at the center, and then Venus is kind of somewhere between us and the Earth, between us and the sun, I should say, you're going to get, depending on where Venus actually is, you might get a crescent Venus or half Venus, or what we call a gibbous Venus. That means a full disk of Venus minus a crescent, so it's kind of a bump. And Galileo's the first one to see that. And Venus, was a goddess, right? So why is Venus, this goddess of ancient Greece, supposed to be imperfect and have changes and stuff? No. Aristotle and the guys in his day, they would have no. They would have said no. But Galileo said, afraid so, just take a look yourself. And that's what his advantage was. He could say, go ahead and build yourself a telescope. He didn't build it. He didn't invent the telescope. Some cat up in Holland invented it. But nobody up there ever thought to look at the stars. Galileo did. And he found all these cool things. So Galileo's the one that made the breakthrough to show that the stuff up in the heavens, it's actually, there's a lot of similarities to things that we know are here on mundane Earth. And Sir Isaac Newton said, all right, if that's really true, then there's the forces that we see here on Earth, gravity, for instance, they ought to control the motion. And when he calculated everything out for the moon, by God, it all worked. It worked exactly. It worked perfectly. So his theory of universal gravitation, it is supremely well verified. It is the law of the universe. And even Einstein's theory of relativity doesn't replace Sir Isaac Newton. It just makes a little bit more complexity in special situations to what Sir Isaac Newton already saw. We'll be studying universal gravitation this whole semester, because there's 4 forces in nature. There's only 4. All right? The 4 forces in nature, 2 of them are in the nucleus of the atom. They exist potentially everywhere, but they only have effects in really compact objects like nuclei. So the force that holds protons together in the nucleus with neutrons, protons are positive, they should repel apart. But the nucleus is held together by what we call the strong nuclear force. And then there's another nuclear force involved, and those appear in the nucleus. All right? Question? No, we're still on this one. I'm still blabbing my big mouth about Sir Isaac Newton. This is all related to him. Yeah. The question was, are the slides supposed to be switching? Not yet. I'll switch it in a minute. We got some more comments coming. But anyways, there's 4 forces in nature. 2 of them are in the nucleus. One of them is gravitation. Gravitation rules the vast reaches of the universe because it's always attractive. It can never be turned off or screened. Electromagnetism is the force by which we learn about objects in the universe through light, infrared, ultraviolet, X-rays, gamma rays. That's all electromagnetic. The The force that holds an electron bound to the nucleus is electrical, not gravitational. And here's a side note for you. And this will be, and I'll change the slide here in just a second. Okay. Last comment about Sir Isaac Newton is that gravitation, it's hugely important, but it actually is by far the weakest force of the four forces in nature. The nuclear force that binds protons and neutrons together is the strongest, then electromagnetic, and then weakest of all is gravity. It's pathetic. All right, a couple more comments. Let's change the slide. Okay, we're still in section 1.3. And that is, new experiments and observations can lead to new... This is just a quote. You can go and read it in the textbook. New experiments and observations can lead to new, more sophisticated models that can include new phenomena and laws about their behavior. The general theory of relativity proposed by Albert Einstein is a perfect example. It's a transformation that took place about a century ago, and it led us to predict and eventually to observe a strange new class of objects that astronomers call black holes. And I know a lot about black holes. It's one of my research specialties. And we'll be talking about black holes from time to time. Now, the guy that I want you to think about in this context is Galileo. Because it was Galileo's insight. Notice the one word in that quote that I have underlined is laws. And Galileo was the one that kind of introduced this whole idea of laws of nature. And here's a quote that I'm going to try to remember it as best. It's pretty close to this. He said that nature is like a grand book. He means the universe. It's continually open to our gaze. The words in the book are written in a mathematical language, the symbols of which are triangles, circles, and other geometric objects. That was his conviction, that the nature of physical law would be mathematical. And that's one of the things about this particular quote here. Since the time of the ancient Babylonians and the Egyptians, astronomers have observed and taken data. They've written stuff down, hieroglyphics, and over there in Babylon with cuneiform writing, And I think astronomers still use some of that data from time to time. They made some pretty good and over thousands of years. But there's a difference between just recording what's happening and having an intelligent explanation of why it's happening. And that is the idea that Galileo kind of introduced. He said, there is a reason. The universe is not random. There are laws. And we humans can grasp those laws if we do diligent observation and measurement, experiment, and if we use a little bit of mental elbow grease and think of the mathematical patterns we may see in the data. So there's a difference between a data set and a data set that has a mathematical explanation. And that's what Galileo's huge contribution was. The whole field of physical science, astronomy, physics, chemistry, all that, is, Galileo's the one that got the whole shebang moving. And just for this concept alone, he's famous. Question?
Is there any evidence that these laws existed before humans were there to observe them?
The laws of nature?
Yeah.
That they existed before humans?
Yeah.
Yes, and
Or did we come up with them?
well, we developed them. The laws of nature are me telling you, here's how it works. And here's the equation. And we're going to use some equations this semester for a few places. Okay? The whole thing about science is observing. figuring it out, and then communicate. It's got to be something you can test and communicate, and somebody else can test and either verify or, disverify. And so, yeah, our conviction is that the universe, the farthest reaches of the universe, works the same way as they do right here in Orlando, And that Sir Isaac Newton's 3 laws of motion apply here in Orlando, down at the ballpark, the same as they do in the surface of the sun and in the core of the sun, in the core of our galaxy, and everywhere across the universe. That's our conviction, so yes. And what you're really asking is that famous question: if a tree falls in the forest and no one's there to hear it, will it make a sound? And my answer to that is yes, of course it will. Sound is an objectively measurable thing. So, question?
And so following that logic, if one looks at the universe and you see the orbiting planets, those same laws are in effect. It's just there are different factors that have to be taken into account.
Yeah, the same laws govern every planet that we see, and we've seen stars orbiting planets. We've actually seen a few of them, and we've detected many other planets. They're called exoplanets, and we'll be studying those for a little bit this semester. And they Sir Isaac Newton's law of universal gravitation, just like that, and it works. It all fits. It all verifies. But we're always alert. We're always alert to something. And that's happened too. Upset the apple cart. You just got to be ready to pick up the apples and find a new cart. Tote those apples around it. So, that happens too. All right, let's keep going. Section 1.4. I want to go through a calculation with you in section 1.4. So let's take a look at this. In the textbook, there's an example where they calculate the number of kilometers in a light year. Now, I want to work out with you the number of kilometers in a light second. All right? And so hopefully this will work well. And this will be a second example to accompany the one in section 1.4 of your text. Now, a couple specs before we begin. The customary symbol for the speed of light is c, as in E equals mc squared. That c squared in there, that's the square of the speed of light. This is the formula, Einstein's most famous formula, for the rest energy of any object in the universe, from an electron all the way up to a galaxy. It will always have energy because of having mass m, measured in kilograms. All right, so that's the customary symbol. The value of it is this. That is nasty. I'm sorry, it looks much nicer on my Mac. It's going to be rocky. That's C equals 3 times 10 to the 8th. And then the smaller symbols are meter per second. M in the numerator and an S in the denominator. And I'm sorry, it looks really good in the Mac, but it doesn't look so hot here. Because this is actually a Microsoft PowerPoint file that you're looking at. And mine is, of course, superior technology. But anyways, let's park this down here. So C is equal to 3 times 10 to the 8 meters per second. All right? And so if you want to know what a light second is, distance is speed times time, right? Okay, so C times 1 second. That'll give you a measure of distance. All right? So go ahead and write this down. C times 1 second, in parentheses. That's my first equation block. And on the right side of the equal sign, it has, in the first parentheses, 3 times 10 to the 8 meters per second. And then the second parentheses, it has 1 second. All right? Now, if we want to do a light year, we'd do something similar, except we'd have the number of seconds in a full year, which you can calculate. 365 times 24 times 60 times 60, and that's how many seconds you have in a year. Okay? And they do that in the textbook. All right? So we're just doing a light second. All right, so there's your calculation there for light second. And let me just point something out to you. The seconds, well, think about that. Look at that calculation. Is there anything in there that looks helpful or nice? The S, who said that? I think dude in the back row, I can't even see it hardly. 16 light seconds away. The S's cancel. Yeah, seconds cancel. In the first parentheses on the right side, you have seconds in the denominator. Meters per second, seconds is in the denominator. And in the second parentheses, you have seconds in the numerator. So they cancel out. Now let's see if this works. Oh man, it's supposed to burn in flame. It's supposed to be flames. It's pathetic. This Microsoft garbage. All right. Anyways, I'll just cross out the S. Cross out one S in the second parenthesis, and then the S in the denominator. Now, you still have that meter in the numerator of the first parenthesis. All right? But that's good because we're trying to figure out a distance. Distance is measured in meters. All right? Now, we want to figure out kilometers, but we'll get into meters, and then we'll convert it into kilometers. Okay? So we're almost there. All right? So 1 light second, and LS is the customary symbol for light second. LY is light year. 3 times 10 to the 8 meters. Okay? Now, that's an 8. Yeah. 3 times 10 to the 8 meters. All right? Now that is the same as 300 million meters. 10 to the 8. That's a 10. See, 10 to the 8 is 10 times 10 times 10 times 10 times 10. Okay, that's 5. Times 10 times 10 times 10. So that's 10 to the 8. Multiply by 10. 8 factors of 10. And then a 3. And that's how many you got in 1 second. All right. Now, so there's that looks better. Okay. 1 light second is 3 times 10 to the 8 meters. Okay. Now, we want to convert that into kilometers just so that we can say that, as far as I'm concerned, if you get a distance in meters, ding, you're fine. All right. But let's convert it to kilometers, so we're kind of doing the parallel task that they do in the textbook. All right. And so 1 kilometer is 10 to the 3rd meters, 1,000 meters. Okay? So so look at my hands up here. Yo, everybody look. Zoop! I got 5 fingers on one hand and 3 fingers on my other hand for 8 powers of 10. All right? Now 3 of them are going to be, is going to form a kilometer. Right? Because a kilometer is 10 to the 3 meters. And then I still have 10 to the 5 over here. All right, so let's look at that. Okay, 1 light second, we know it's 3 times 10 to the 8. But that's the same as 10 to the 5, 3 times 10 to the 5, times 10 to the 3 meters. All right, now that 10 to the, okay, so this is the 3rd equation block. And that 10 to the 3 at the end is a kilometer. So we can just, in our next line of the equation block, we'll just write in the symbol Km. How about that? All right? So 3 times 10 to the 5. Kilometers. Right? 3 times 10 to the 8 meters. 3 times 10 to the 5 kilometers. All right? So 10 to the 8, when you convert to kilometers, you're hiding these 3 fingers, for these 3 powers of 10 from my right hand, you're hiding them in the symbol K for kilometers. All right? But it's the same number. And so if you're doing a written test and I see you write it down like this, or even if I see you write it down like this, 300,000 kilometers. If I see that, that's good. I'll give you full points for any of these. If it's a written test. Now, when we're doing calculations on exams And in lecture, we'll probably start doing some of those next week, some cinchy ones. You'll be entering numbers with your eye clicker. And then I'll tell you how to answer. I'll tell you, okay, give me to the nearest 10 to the 5 meters. So you'd write in, okay, 2.7 or whatever the answer is. And then you hit the send button. Okay? So on iClicker, I'll tell you. But if it was a written exam, all three of these versions would be fine. You know, unless I tell you to answer in kilometers, then only the last two over there on the right are fine. Anyway, so let me pause for questions. Yes, over here. What's that? I can't exactly hear what you're asking me.
Instead of separating it by the 3 ways, you separated it into 2 sets of 3, and then you have 2 of them.
I could have. So you're saying of my 10 to the 8, take 3 here, and then take 3 here, and I'm left with 10 to the 2. So that would be, so then I have to have a symbol for 10 to the 6. Okay, and what is 10 to the 6? 1,000,000. So that would be a megameter. Now, we don't usually use megameters, but that's what it would be. And so this one would be 300, 3 times 10 to the 2, megameters. Okay? All right, and what is your name? Mirthalon? Okay, Mirthalon. 300 megameters would be perfect. I would go ching, and you get full points on that. And so yeah, I mean, the powers of 10, you can separate them and recombine them till the cows come home. Just whatever you think is good. You know, and some astronomers, they use kilometers, some use meters. I've even seen astronomical stuff in centimeters. So it just depends on what you want to do. Another question before we continue. Yes, Cameron.
Technically, you think of it as like multiplying by 1,000 because a kilometer
Yeah.
is
A kilometer is 1,000, so that anytime you see a kilometer, you can replace it with 10 to the 3 and then the symbol M for meter. Because that's what a kilo means, 1,000. Samuel.
I understand what she's asking actually, but like as you can see, these aren't in squares, so that's why you don't do 6.
Oh, you were thinking about square kilometers. Yeah, it's not an area, it's a distance. It's not an acreage. Right now, if we were doing that, yeah, then we would have to use your strategy. But okay. All right, let's keep going. Section 1.5. And this one features, I believe it has a picture of the Hubble Space Telescope. It talks about light years and distance. And here's a quote from it that I like a lot. For a star 500 light years away, the light we detect tonight left 500 years ago, and it's carrying 500-year-old news. Now that is pretty old news. I mean, yesterday is old news for most of us in the internet age, but 500-year-old news is kind of hokey. But the thing I like about it is that sentence describes light as carrying information, news. And that is significant. Okay, so I want you to write down the upshot here, which is that electromagnetic waves, they don't propagate objects. You know, a baseball propagates through space when you hit it towards the outfield or hit it to first base or something like that. And it carries momentum and energy with it. But waves don't do that. Electromagnetic waves, they propagate or transport energy and momentum, but also information. Now, Sir Isaac Newton could have talked about energy and momentum. But only after Einstein developed the theory of relativity, and in fact Stephen Hawking and a bunch of other guys developed the laws of black holes, do we think about the information content of electromagnetic radiation. It is a significant idea. Now, another thing that I want to mention in 1.5 is the idea of a light cone. Okay, now there's a light cone is two cones tip to tip like that. And I'll tell you about how that works after this quote, also from 1.5. There's the light cone. Okay, and here's the quote. But what at first may seem a great frustration, in other words, 500-year-old news, you're out. It's actually a tremendous benefit in disguise, because by looking billions of light years out into space, really faint galaxies that we see out there, astronomers are actually seeing billions of years into the past. Yeah, you're getting news from billions of years ago, almost to the time of the Big Bang. In this way, we can reconstruct the history of the cosmos and get a sense of how it has evolved over time. Now, I want you to try to draw a light cone. It's two cones, tip to tip, and try to draw it in perspective the way that I have it, if you can. And right here where the two cones meet tip to tip, that is a galaxy. Let's say that that's a galaxy. And a light cone is a way of telling or of modeling everywhere. The time in this picture, time is going upwards. Okay, so later times are higher in the diagram. Earlier times are lower in this diagram. So the time axis is horizontal, or is vertical. The spatial axes are left and right, forward and back. Okay, so everything inside this cone, this is the future light cone. Let me get my cursor. This one right here, this upper one. That's the future light cone. Okay? The galaxy can send spacecraft and light forward into the future. It can't go faster than the speed of light. So the edge of this cone marks the place where light traverses. Light rays going outward in all directions will form the boundary of this cone, the surface of the cone. Everything else, spacecraft, baseballs thrown away from that galaxy, spitwads, everything will be somewhere inside, either close to the light cone, the faster they are to the speed of light, or, near the time axis if they're going really slow. Right, a light cone. Now, the lower light cone, which is this one down here, and we'll talk more about these when we get to black holes. The lower light cone is all the region of space-time that can have an effect on the galaxy before it turns around and sends things into the future. All right? So this light cone, and we'll talk about it more when we talk about black holes, because when black holes are involved, light cones go all over the place. This is just standard light cone here. Nothing fancy about this one. And so for us, for an astronomer, we're not dismissed yet. We still have a few minutes of lecture. I have more comments. The history of the universe, you can read it by catching light from light cones far, far away, from galaxies far, far away. We're catching their light cones. And so the farther away it is, the dimmer it is, and the bigger a telescope you need. So we keep building bigger and better telescopes, and we keep seeing more and more galaxies out there. It's pretty cool. We're seeing way back into history, about 13 billion years, we think. Okay, section 1.6 comments, and we'll finish with this one. The moon's distance from Earth, this one's telling about the distances. Oh, sorry. I'm operating two computers up here, so it's a little bit shaky. All right, so there's the light cone ideas that I talked about. All right, section 1.6. The moon's distance from Earth is about 30 times Earth's diameter, or 60 radii. Sir Isaac Newton knew that. It's approximately 384,000 kilometers. Sir Isaac Newton didn't know it to that precision, but that's what we know it today. It takes about a month for the moon to revolve around Earth. Sir Isaac Newton knew that, to the fraction of a day. The moon's diameter is 3,476 kilometers, and Sir Isaac Newton could estimate that as well. You know, working out the geometry and stuff. Trig. It's about 1/4 the size of the Earth. Now, I'm going to give you a little blurb about the scale of the solar system. All right? If you make the Earth an image on your computer screen 100 pixels wide, which I sometimes do, then the moon's size would be 25 pixels. It's a quarter the size. All right? And that's what it says in the quote, 1/4 of the size. And the distance is 30 times Earth's diameter. So if Earth's diameter is 100, then the moon's distance is 3,000 pixels. Now, my MacBook up here doesn't have 3,000 pixels. It has about 1,800 across. Okay? So a big computer screen might have 3,000 pixels across. And that would be good at this scale. Make the Earth the size of 100 pixels in a little circle, and then a moon 25 pixels across, good, and park them 3,000 pixels apart. And that will be to scale. And in section 1.6, they give you a scale diagram of Earth and Moon. The sun is 500 light seconds. Now, it's about 1.3 light seconds from Earth to the moon. And from Earth to the sun, it's about 500. Now, write this down. 500 light seconds from Earth to the moon in reality, in the scales here, 1,000 pixels for Earth, the sun would be 1,167,000 pixels away. All right, on the scale of my computer screen, which is about 75 pixels per inch, what that would do is put the sun somewhere on this circle. All right, now here we are in the center. Here's the big version. Here we are at Visual Arts, right about here at the center here. All right? Right now, that means that if the Earth were 100 pixels wide on my computer screen, the sun would be out there on Alafaya by the light that turns in at the music building. That's the music building, yeah. All right? That's where the sun would be. Or it would be all the way over at the Student Union. Or it would be, down here. I don't know, what's down here? This is like the reflecting pond down here. There's the reflecting pond. Yeah, that's where the sun would be. If the Earth is 100 pixels, and I'm not even going to tell you how big the sun would be, but that's how far away it would be. All right, it's 2:50. Let's dismiss. Look for some homework, reading by lunchtime Thursday, and I'll see you next week. You're dismissed.